This is the next video in the series about the next generation science standards, and in this one I'm going to explain to you the architecture of the NGSS standards. That should give you a clue right away. When you have to call a standard or describe its architecture, and that tells you it's going to be pretty complex. In this video I'll explain the differences between the NGSS and the 1998 California Science Standards that we are currently using and will be phasing out after next year. And I'll illustrate how these standards shift our thinking and instruction in science. Now remember this image from the first video? I picked this one deliberately because I said it really proves how overwhelmingly complex the NGSS standards can look. In fact, if you look at all the parts together, like you see it here, it could make you cry. But in fact, they're relatively simple to understand when you think about it this way. The standard is actually a performance expectation, and that states what the student's performance should be. That is the assessed part of the standards. That performance expectation has three parts: a science and engineering practice, a disciplinary core idea, and a cross-cutting concept, all combined together to make one performance expectation. So here, let's look at them together. The performance expectation, for example, in second grade physical science on matter and its interaction says that the student will construct an argument with evidence that some changes caused by heating or cooling can be reversed and some cannot. Now notice that this performance expectation rests on the foundation of a science and engineering practice. That is, that students should construct an argument with evidence. Scientists and engineers construct arguments with evidence, so students must. The performance expectation also rests on the foundation of a disciplinary core idea that changes caused by heating or cooling can sometimes be reversed and can sometimes not be reversed. Scientists and engineers know that this is one of the core ideas of physics, so our students must learn it as well. And the performance expectation also rests on the foundation of a cross-cutting concept, or a big idea, that some changes caused, there we have cause and effect. Cause and effect is a big idea that scientists work with in all the science disciplines, not just in physics. Every performance expectation has these three dimensions, just like the one I showed you as an example. In the 1998 California Science Standards, it states that a second grade physical science standard is students know magnets can be used to make some objects move without being touched. It's about magnetic force. The difference? What students must know, students know magnets blah blah blah, versus what students must know how to do, construct an argument with evidence using science knowledge. A shift is required to teach the NGSS in that science education now has to reflect real-life interconnected science. Scientists and engineers use science and engineering practices, work with core ideas from the science disciplines, and use concepts that cross disciplines to connect their practices and ideas. So then, to teach the NGSS, we need to use real-world science and student-centered inquiry so that students are engaged as scientists and engineers, doing what scientists do, discovering what scientists know, and thinking how scientists think. Because the three dimensions are more perhaps not commonly, but more naturally thought about as the things scientists do, the things scientists know, and the way scientists think. Here's an example. I'd like you to think about this. Can heating and cooling be reversed? Use the example in front of you and talk it over with someone. Using this example, you probably have some ideas, some answers to whether heating and cooling can be reversed. But now I want to add another piece of evidence. Can heating and cooling be reversed? This is a piece of paper. If you use the data from the last picture and from this picture, now you're probably thinking about different variables of what it means to heat or cool something. And you're also looking at different properties. How about this? Can heating and cooling be reversed? I'll stop you here, but what I want you to see is that just by asking the question based on the performance expectation, I hope to get my students to be thinking about what they already think they know about heating and cooling and whether or not it can be reversed. This is just an engagement into the ideas. Lots more learning to come. But already students have ideas about how the world works. They have cause and effect ideas. And they might be incorrect. And we've started to make them think about them and construct an argument with evidence based on what they know about heating and cooling, and then different properties of different objects. And then I would have to teach more, of course, getting them into some of the more scientific principles, the disciplinary core ideas. If you noticed anything about the role of the teacher, it was that hopefully I was relatively silent while the talking was done by students. The role of the student is to be involved in inquiry, in discussion, in arguing, in using evidence, doing a lot of the thinking and inquiry on their own. In the next one, I'll talk to you about how the NGSS will impact science teaching in Tracy Unified School District. Thanks for listening.